through encryption. SChannel is primarily used for internet applications that require secure hypertext transfer protocol communications. Okay, secure channel. Secure channel, also known as SChannel, is a security support provider (SSP) that contains a set of security protocols that provide identity authentication and secure private communication through encryption. SChannel is primarily used for internet applications. Yeah. For more information about secure channel, see the following topics. Message authentication codes. Message authentication code (MAC) is used to detect message tampering and forgery. The sender of a message creates a MAC message authentication code by encrypting a one-way hash of the message body using a session key shared by sender and recipient. The MAC is appended to the message that is sent to the recipient. The message recipient generates the MAC again using the shared session key and message body, and compares the generated MAC to the MAC received from the sender. If the two are identical, then the sender must have the shared session key and the message has not been altered in transit. In SChannel protocols, the algorithm used to generate the MAC is determined by the cipher suit in use by the sender and recipient. The cipher suit. Cipher suits in SSL, TLS, SSL, SChannel, security. A secure channel, I think. Cipher suit is a set of cryptographic algorithms. Channel SSP implementation of the TLS SSL protocols use algorithms from a cipher suit to create keys and encrypt information. Cipher suit specifies one algorithm for each of the following tasks. Yo TCAP, what's up? Thanks for the raid. Welcome everyone. Yeah, thanks. So what's up guys, what's up? Salam. Alaikum salam. Yeah, welcome chat. So today I'm just continuing work on my bot because last stream I started like a chatbot in C. But it requires TLS, so I'm reading about TLS encryption on Windows. Greeting friends of realizing SChannel is not about perfume. That's funny. Yeah, so I have an example here, which it's just using Windows, basically Windows libraries to do the TLS handshake. Perform TLS handshake, you know, only using TLS like Windows security, doesn't use any third-party dependencies. I guess let me show you what it does for now. No, I'm 23 years old. So right now it runs and it gets the HTTP reply from the Twitch, but of course Twitch requires HTTPS, so it's giving me 400. Plain HTTP request was sent to HTTPS port. Guys, is there any lag or something on the stream? Is my voice at a good volume? Okay, nice. Yeah, so it's just a plain HTTP. But yeah, we require TLS. I'm actually just learning about TLS right now. Yeah, so Windows has this thing called SChannel, which is a security support provider, SSP. SChannel credentials. SChannel protocols require credentials to authenticate servers and optionally clients. Server authentication, where the server provides a proof of its identity to the client, is required by the SChannel security protocols. Client authentication may be requested by the server at any time. So SChannel credentials are X.500 lines certificates. Public and private key information from certificates is used to authenticate the server and optionally the client. These keys are also used to provide message integrity while client and server exchange information required to generate and exchange session keys. For programming information, see obtaining SChannel credentials. Credentials are required by the SChannel authentication process. Both client and server must obtain valid credentials to establish a security context for message exchange. For an example that demonstrates this procedure, see getting credentials. Getting credentials. The application obtains credentials by calling the acquire credentials handle function, which returns a handle to requested credentials. Because credential handles are used to store configuration information, the same handle cannot be used for both client-side and server-side operations. Guys, have you ever done something like this before? It's my first time doing anything with TLS, like from scratch or something. But I've done some encryption, like AES encryption, RSA. I kind of know how that stuff works. Acquire credentials handle. Acquire credentials handle cred SSP function acquires a handle to pre-existing credentials of a security principal. Right, so how does TLS handshake? How does TLS handshake work? Let's see, guys, let's see.
Solid. I'm hollow.
Accept all. SSL versus TLS.
Nothing behind my eyes. I'm a negative of a person.
SSL, or secure sockets layer, is the predecessor to TLS.
I never
It was a cryptographic protocol developed by Netscape in 1994, but since it had serious flaws, it was never released to the public. SSL 2.0 was released publicly after 1 year later, but it too was found to have serious flaws. Finally, SSL 3.0 was rebuilt from the ground up and released in 1996. Microsoft, who had its own version of the protocol, okay, this is just history basically. So let's see how it works. TLS handshakes. The exact steps of the TLS handshake will depend on which TLS version is supported by the client and server, as well as which parameters they are set to use. Yeah, too much yapping, bro. Too much yapping. Since most modern browsers still support TLS 1.2 and a lot of websites still use... yeah, okay. So this is how it works. TLS 1.2 can be configured to use many key exchange algorithms, and among them, the most well-known and widely used is RSA key exchange algorithm. So RSA is like... I've used this before. So it's the one where they, like, you have a public and private key, and you encrypt with the public key and decrypt with the corresponding private key. And the private key is like it's two large primes that are multiplied together. That's all I know about it, but it's like asymmetric encryption. Yeah. So yeah, it can use many key exchange algorithms, and one of them being RSA. Yeah, let's go over how the RSA algorithms works in 1.2. So the RSA key exchange works roughly as follows in TLS 1.2. Server listens for new connections on port 443. Client connects to port 443 and initiates the handshake process with a client hello message to the server. Interesting. This message contains the TLS versions and cipher suits the client supports, and a 32-byte random number known as client random. The server says hello back with the server hello message. Server selects a cipher and the TLS versions from the list provided by the client. Okay, server says hello back, and it selects a cipher and the TLS version from the list provided by the client, then generates a different 32-byte random number known as server random, and sends it back along with the server's own SSL certificate. So SSL is what they were talking about, which is secure socket layer. Client uses SSL certificate to verify the server's identity. SSL certificates contain public key generated by the server and a digital signature signed with the private key of a trusted third party known as a certificate authority. Yeah, so it has a public key generated by the server and a digital signature signed with the private key of a trusted third party known as a certificate authority. Most web browsers and operating systems come bundled with public keys from trusted CAs. Okay. Which are used to verify that the CA issued the certificate. Okay, so we use the OS's basically public keys to check if that certificate is valid from the server. Client verifies the server has the matching private key to the certificate through client key exchange. Client verifies the server has the matching private key to the certificate through client key exchange. Client generates the pre-master secret, a 48-byte random number, and encrypts it with the server's public key obtained from the certificate. If the server is the true owner of the certificate, it must be able to decrypt the message and obtain the original pre-master secret. Wait, let me read that again because it's confusing. The client generates the pre-master secret key, a 48-byte random number, and encrypts it with the server's public key obtained from the certificate. If the server is the true owner of the certificate, it must be able to decrypt the message and obtain the original pre-master secret. So it's just a random number, I'm guessing. And you encrypt it with the server's public key obtained from the certificate. See some diagram of this. Open image in new tab. Okay, it sends hello, client hello, and we get server hello certificate and server key exchange. Okay, no, this is bad. Let's maybe see a video about it. It's like TLS handshake.
Last time we looked at TLS and we had a bit of a chat about where it came from, the history and how it evolved. So I suppose we're left with the idea of working out how it works and that handshake procedure, right?
That's right, yeah. Everything in TLS happens in the handshake. I mean, that's not absolutely true, but you know, the majority of all the important stuff is in there. The reason that TLS is so prevalent and so used and how good it is all down to how good the handshake is. So let's dive right in and see what it is that it does underneath. Today we're going to look at the TLS 1.2 handshake, not the TLS intuitive when you're learning it for the first time. If I click on the padlock and I click more information, we can see that I've got a TLS session. So my computer, my browser in this case, and the Nottingham web server have formed a TLS connection that sits over TCP and is encrypting HTTP before it gets sent and received. Now, what I'm interested in is this string down here. So we're just going to copy that down, and then we'll talk about what that is. And then when we look at the handshake, you'll see all the...
This is the suit that they were showing the other. Yeah, here. It's the cipher suit, so yeah, this is the protocol they're saying. Then key exchange algorithm. This part's the key exchange algorithm. This one's the authentication algorithm. Yeah, and this is the symmetric encryption algorithm. It's AES 128 GCM. And the last part is the hashing algorithm. So yeah, that part is
appearing, because basically this is what we call a cipher suite. So this is a string representation of all the different things we're going to do during our handshake. Right? So for example, key exchange, public key authentication, the actual encryption and things like this. Right? They're all in there. So let's have a quick look. I'm going to bring up the ink pad thingy. Oh, this is here from last time. All right.
Last time we used this app.
Yeah, okay. Yeah, this is only for recording videos and stuff, so, you know, when I'm not recording videos, I'm not really using it, I just use my computer. Alright, so let's take this off. There are a few different cipher suites, but the one we're looking at today is the most common one, and that is TLS, EC, DHE, RSA, with AES, 128, GCM. I've run out of space. SCHA256. It was impossible to know when I started at that font size that it wasn't going to make it all the way to the end. Right, there's a lot of stuff going on here. So let's have a look at these. Right, so TLS, we know what that is, right? That was the whole last video. Transport layer security, you got two or three. ECDHE, that's elliptic curve Diffie-Hellman ephemeral. Right, we've talked about Diffie-Hellman before. That is the key exchange. So that is how we obtain some kind of shared secret.
Yeah, I understand everything in this except the key exchange thing. I know what AES is. It's basically a block cipher. It's advanced encryption. I think advanced encryption system, something. And the SHA is secure hashing algorithm. And GCM is something to do with AES, basically. It makes it more secure or something.
Only you and I have, or only me and the web server has, so no one else can see what we're doing. That's obviously going to be used to derive keys for encryption. RSA, this is going to be the public key authentication mechanism. Right, so we're going to be making sure that that server is who they say they are by checking a public key certificate and verifying their digital signature. And then when we've actually done that, that's the handshake part, then the actual encryption is going to be happening using AES. So this is the cipher. This is the key size. This is the mode of operation. So this is going to be Galois counter mode. I think I might have mentioned that in a previous video, but if I didn't, it's a whole different video. And finally, SHA-256, that we talked about hash functions before, is the kind of the building block that's used to perform hash functions where they're needed. So things like turning a secret into a key and creating message authentication codes and things. These are some things we've covered in other videos.
So SHA is just, it's literally just a hashing algorithm. So you give it a block of data that's like, it can be any size, and it gives you a fixed size hash for that. And it's used for, you know, passwords, for integrity checks, you know.
Yeah, and we've got only a few messages to get this done, right? Because it's got to be really, really quick. So let's go through the actual handshake, and then we'll see some of these things appearing. We're going to start a conversation over the internet. It's going to be with someone using TLS. So we begin obviously with a TCP handshake to get a TCP connection established. And before we send any application data, that's when we're going to do our TLS handshake. So this is the client over here, and this is the server over here. I'm going with client and server this time, not Alice and Bob. It would work just as well with Alice and Bob. If you think about the way the web works, the client is always the one approaching the server. Amazon, well, for the most part, doesn't just send you random websites. Right? You ask for a website and it gives you one, or you ask for a file and it gives you one. So the first thing we're going to do is send a message, and that message is called client hello. We know what that message is because All TLS messages have a number that identifies them, and so basically you can read off the header and you can work out what kind of message this is. Now this client hello message is going to contain a few things. First of all, it's going to contain the max TLS version that this client can support, because obviously you've got different servers, you've got different clients, so it's going to be the max TLS version that they support. Not every server and every client is exactly the same. They won't all support the very, very latest version, so they maybe don't support 1.3, so maybe they send 1.2, but that's the maximum version they support. They're going to send a random number, and that's used to make sure that replay attacks, for example, aren't going to work. And finally, they're going to send a list of cipher suites. So that cipher suite we looked at just before, there's going to be a number of those that they support, probably, and they're going to send a list of all of those. Each of them has a number, so it's a nice short list. Mm-hmm. Assuming the server's switched on, right, that's a whole different problem. Right, so I'll rub that out. Right, so we've got the client hello. So at this point, the server knows what the client can do, and now it has to pick something. Right? The way that TLS does it is that the server is the one that actually chooses. As a client, you go to the server and you say, I can do these things, and it says, right, we're going to use that one. Right? So the server is going to respond with a server hello. Now, that's going to contain very similar things to what the client hello contains. So it's going to have a chosen TLS version, right? So let's say the client supported 1.3, but the server only supports 1.2, it will send back 1.2. Right? It's going to choose one of the cipher suites, and usually it will have some kind of configuration and which ones it prefers and things like this. And then it's going to also send a random number. Right? If the server doesn't support any of the versions or the cipher suites that the client does, which is very unusual, then obviously this is not going to work. They're going to send back some kind of failure message, right? They'll actually send back a TLS alert, and that will say, yeah, it's not going to work, right? We won't be having a conversation. All right, so this is the beginning of the handshake. We now know what we're going to do. We're going to use, let's say, elliptic curve Diffie-Hellman, we're going to use RSA, we're going to use AES when we eventually get to encryption. Right? So now we actually have to do those things, unfortunately. So the server's going to send another message, and this is going to be a certificate. Various videos have talked about public key certificates before, but this is just going to be a standard format certificate with an RSA key, if that's what we've agreed to use, and it's going to crucially have a public key on it. Right? So this is going to have a public key attached to it. The server's then going to send what we call the server key exchange message. That has a few things in it, right? The first thing it has is the parameters for the Diffie-Hellman key exchange, right? So we talked about the parameters G and N way back when we did the video.
Alice and Bob have to agree some mathematical parameters that they're going to use. This is a value G, or a generator, and a big prime number N. Right? Now, for this,
it's going to choose some of those, possibly elliptic curve ones, probably, because that's what we're using. And it's also going to send its public message as part of that key exchange process. So if you remember back very briefly in Diffie-Hellman, you each send a public value across, and then you combine it with some private values behind the scenes.
This is all the coloured water video we did, right?
That's the coloured water video, yeah, which kind of works, yeah. The server key exchange also, very importantly, has a digital signature as part of it. So I'm going to write that in, digital signature. Now, a digital signature is essentially a set of these previous messages summarised using a hash function and signed using the private key of the server, the one that goes with the public key that's on the certificate. It's the proof that the server is who they say they are, because only theoretically that server has the private key. Right? We've covered these kind of things before on different. I think Rob did a video on public key.
The fact that it can be decrypted with your public key means that it must have been encrypted with your private key, which means it must have been you who made the message, because only you have your private key.
What the client's going to do is it's going to look at the certificate, it's going to verify that that's okay, and then it's going to look at the digital signature and verify that's okay using the certificate. And if they're both okay,
wait, what did he
as
say?
a client, covered these kind of things before on different. I think Rob did a video on public key.
The fact that it can be decrypted with your public key means that it must have been encrypted with your private key, which means it must have been you who made the message, because only you have your private key.
What the client's going to do is it's going to look at the certificate, it's going to verify that that's okay, and then it's going to look at the digital signature and verify that's okay using the certificate. And if they're both okay, as a client, we can be pretty happy that the server is who they say they are. Right? This is almost, for me, the most important message, right? Because if you can't establish that the server is who they say they are, then this could be a complete imposter, and then we've got a real problem. So there's also the video that Richard Mortier did on Secure Web, where he talked about you follow this chain of trust all the way up to a certification authority. That's the process that this client is going to follow. So at this point, the server's sent their part of the key exchange. They've sent their digital signature and their certificate, so they've verified themselves. Their job for now is over, right? So they're going to send a server, hello, done. And that says, I'm not sending you any more weird information, right? You've got everything you need, right? If you're not happy, that's unfortunately just how it's going to be. So it's now the client's turn, right? So the client, as you remember, in the key exchange, you've both got to send something, right? So the client is going to reply with a client key exchange. Now, normally the client doesn't send a certificate. They don't have to send a certificate verification or anything like this, a signature. And they, of course, already have the parameters that the server sends. So all they're going to send is their Alice public value, right? The one that goes in over here. These can be used mathematically as part of a Diffie-Hellman process to create what we call a pre-master secret. So at this point, the server and the client both have the same pre-master secret, right? They combine that pre-master secret with the random numbers from above, and that becomes the master secret. Right, and that's the one that's used to derive any kind of key material that's going to be used during this process. This is looking kind of complicated, but actually we're nearly finished. Right? This doesn't take a very long time. The client is now going to send a change cipherspec message. What the change cipherspec message says is, I've got all the information I need from our previous handshake. I'm actually ready to begin encryption. Right? So the next message you see from me is going to be encrypted, right? Using all this, right? Using AES. 128-bit key, Galois counter mode using the key that we just derived, and so on. So they're then going to send a finish message, and that finish message is going to contain a summary of all of the messages so far encrypted, right, using the key, right? So obviously, if this process has failed, the server's not going to be able to decrypt it. The server's going to respond with the exact same thing. So they're going to send over this way a change cipherspec, right, and then a finish message, which will be encrypted. Now, the really important thing about these finish messages, which didn't used to exist in the really early versions of SSL, is that they summarize all the messages seen so far. So imagine someone was sitting in the middle, tampering with the messages. Maybe they tricked the server into thinking the client actually only supported 1.1. Right? Well then, the client and the server are going to have seen different versions of events, and that means that these two finish messages aren't going to match. So if they don't match, bail from the conversation, jump out the nearest window. Right? It's not good times. Let's look back at what we wanted from this and work out where we got it. Right? So we wanted some kind of...
I get it. Honestly, I get it. The only thing that I don't get is the key exchange. Key exchange... Not really sure. I guess it's a way to securely send the key over from server to client or vice versa. So that's what I'm look up next. Signatures and key exchanges.
Encryption. So let me show you how that works. We're going to use Pam and Jim. They're going to use asymmetric keys to securely exchange data with one another. Now, since these two are two different people, they each have their own set of public and private keys. Pam has one set of public and private keys. She has her public key closer to Jim, available to Jim if he needs it, and she has her private key hidden, private from anybody else. Jim also has his own set of public and private keys, and let's say Jim has a message that he wants to send to Pam securely. Well, what he can do is use Pam's public key to encrypt that message. Now, the only key in the world that can decrypt this back to the original message is the correlating private key, which only Pam has, because again, the private key is never shared. That message can be sent across the wire safely, knowing that only Pam has the required key to decrypt the content of that message and extract the original plaintext. And this is how asymmetric keys are used to provide confidentiality. Recall that confidentiality is the idea that the data is only accessible to the intended recipient. and we can use an asymmetric key pair to ensure data confidentiality. But that's not all you can do with a set of asymmetric keys. There's actually something else you can do, which is pretty cool. Let's say Pam now has a message for Jim. Let's say for this particular message, Pam doesn't care about the confidentiality, meaning she doesn't care who can read this message. But she definitely wants to prove that it was definitely her that sent this message. What she can do is use her own private key to encrypt that message. Now, the only key in the world that can decrypt that would be her public key, which Jim has and anybody else has because it's a public key. So this can get sent across the wire, and then Jim can decrypt that message using Pam's public key. If Jim can decrypt the message successfully with Pam's public key, this actually proves two things. First, it proves that Pam must have sent that message. This gives us authentication.
Wait.
If decrypt that would be this else you can do,
Let's
which is pretty
repeat that.
cool. Let's say Pam now has a message for Jim. Let's say for this particular message, Pam doesn't care about the confidentiality, meaning she doesn't care who can read this message. But she definitely wants to prove that it was definitely her that sent this message. What she can do is use her own private key to encrypt that message. Now, the only key in the world that can decrypt that would be her public key, which Jim has and anybody else has because it's a public key. So this can get sent across the wire, and then Jim can decrypt that message using Pam's public key.
I see. So you'd put like something obvious in the message, and then if it decrypts to what Jim is expecting, then he knows that it is coming from Pam, basically.
If Jim can decrypt the message successfully with Pam's public key, this actually proves two things. First, it proves that Pam must have sent that message. This gives us authentication. If Jim was able to decrypt something with public key, it proves that the only key that could have encrypted it was Pam's private key, and Pam should be the only person that has that key. Therefore, we know Pam sent that message. It also proves something else. It also proves that the message was not modified in transit. That is integrity. If someone captured the message in the middle and changed the content of the message, well, when Jim tried to decrypt it with Pam's public key, he would end up with a jarbled mess if the decryption would have worked at all. So if Jim was successfully able to decrypt a message with Pam's public key, then we know for a fact the message hasn't changed since Pam encrypted it with her private key. This process that we just discussed is what's known as message signatures. You can use an asymmetric key pair to create a signature, which provides authentication and integrity for what was signed. So, we just talked through how you can use an asymmetric key pair to provide both encryption to get confidentiality and signatures to get integrity and authentication. But in reality, it's not quite that simple. Remember, in the last lesson, we talked through a bunch of limitations that asymmetric encryption has. Namely, that it's inefficient to use asymmetric encryption for bulk data transfers.
Yep.
Because asymmetric encryption is...
That's why they use AES, right? Because basically the asymmetric encryption, it works like let's say you're using RSA 2048, right? So you have your public key, which is sorry, the private key is 2048. The public key, I don't know. I think it's typically smaller. So, but anyway, the important thing is that when trying to encrypt data with RSA, it's gonna be the size of your private key, which is 2048 bits, and divide by 8. That's how many bytes you can encrypt with it. you know, the encrypted data is always a fixed size because it's really just an integer that's like that many bits in memory. But something like AES is a block cipher, which means that however many bytes you encrypt with it, that's how many it's gonna be in the encrypted. Like it's 1-to-1 between decrypted and encrypted in terms of size.
Slower
So, yeah.
and more taxing on the CPU. Instead, if we want to actually protect bulk data, what we want to be doing is using symmetric encryption.
Yep.
But symmetric encryption has this problem that we have to first establish a symmetric key on either side of the wire. And we have to do it in a secure way. Well,
Yep.
that symmetric key is a pretty small piece of data. And recall that we can use asymmetric encryption for smaller, limited datasets. Well, why don't we use an asymmetric key pair to share a symmetric key? That is what SSL and TLS actually do. Let me show you how it works. Pam is going to randomly generate a symmetric secret key. This key is just a string of ones and zeros, and Pam will generate them randomly. Pam will then take Jim's public key and encrypt that symmetric key. The only key in the world that can decrypt this back to the original symmetric secret key is Jim's private key, which only Jim has, which means Pam is safe to send that across the wire. Jim will then take his private key to decrypt the content of that message to extract the original symmetric secret key. And now both parties have established a symmetric key that is identical in a secure way. They can use that symmetric key to protect bulk data. Here, Pam has a message for Jim. Pam will encrypt that message with her symmetric key. The only key in the world that can decrypt that message is the same symmetric key that was used to encrypt it. That message can be sent across the wire, and then Jim can use his copy of the symmetric key to decrypt that message and extract the original content. This can be done in either direction for an arbitrary amount of data. Here, Jim is sending something to Pam securely using that same symmetric key. Now that both parties have the identical symmetric key on either side, they can continue to use that for however much data that they want to protect. This concept that we just discussed is referred to as hybrid encryption. Hybrid encryption is the idea of using both. Using hybrid encryption in this way gets you the best of both worlds. You get
Weaknesses, slower, ciphertext expansion, more secure. And symmetric is like faster, but they're saying it's less secure. I don't know why. I think it's just some yapping.
the strength of asymmetric encryption that you have used the more secure bulk data transfer. To take
So I get, now let's go back to the example code. So okay, they have a socket, cred handle, context t handle, security package context, stream sizes, and incoming TLS max packet size. Interesting. So they have this function TLS connect, TLS socket, and they have they're passing it the hostname and the port. They're initializing Windows sockets. This is basically the same code that I had. They're creating, yeah, same thing, like socket create TCP IPv4 socket. So here they're doing it a bit differently. They're directly creating an IPv4 socket. But here I'm like querying first querying all the addresses for that port, that host name, all the IP addresses associated with it. Connect to server. Okay. Acquire credentials, handle A. Yeah, this is the SChannel credentials that we're reading about. So he's setting the version and he's setting some flags. Like SChannel use strong crypto. SCH credential, auto credential validation. Automatically validate server certificate. And SChannel cred no default credentials, which is no client certificate authentication. And grabit or grbit enabled protocols, which is here they're setting it to TLS, only TLS 1.2. Okay, so let's I guess make our own similar function to this, I guess. Static int TLS connect. They have a struct here. TLS socket. Sock. Cred handle. Let me put some music again. Cred handle, context, T handle. Security package context. Stream sizes. Int received, int used, int available. Our pointer decrypted. Let's type def sideChar to byte. It doesn't make sense to use char when we're dealing with unsigned bytes, you know. Income. Find TLS max packet size. Payload plus extra overhead for header MAC padding. Probably an overestimate. 16. 512. Plus extra overhead for header MAC padding. containing SChannel credentials. Getting a certificate for SChannel. Cert open store. This doesn't even use that cert open store function. Interesting. Creating a security buffer, size 2. Buffer type, security buffer token. It's pointer to the buffer, which is socket incoming. And count is this buffer type. Sec buffer empty. And that's the second one. So in buffers at index 1 is empty. There's also out buffer, which is a token. Use supplied creds, allocate memory, confidentiality, replay detect, sequence detect, stream. What's move memory? Is that just like a move? Yeah, it's the same as C's mem move. Okay. S handle, cred handle. Secure channel, security support provider. TL socket S on char host name 16 port Handshake and cipher suit negotiation. authentication of parties. Makes sense. And then key-related information exchange. Establishing a secure session by using TLS. Client sends a client hello, yeah. Server responds by sending a server hello message to the client along with the server's random value. Yeah, so they both send the random values to each other. The server sends its certificate to the client for authentication and may request a certificate from the client. Okay, if the server has requested a certificate from the client sends it. Client creates a random pre-master secret and encrypts it with the public key from the server's certificate, sending the encrypted pre-master secret to the server. Server receives the pre-master secret. The server and client each generate the master secret and session keys based on the pre-master secret. Client sends change cipher spec notification to the server. Yep. Yeah. Server receives change cipher spec and switches its record layer security state to symmetric encryption using the session keys. Server sent, server finished, message to the client. And now clients and server can now exchange application data over the secure channel they have established. All messages sent from client to server and from server to client are encrypted using a session key. Interesting. TLS record protocol. Damn, this is so it's like a whole science to this TLS system. Core protocol secures application data using the keys created during the handshake. Dividing outgoing messages into manageable blocks and reassembling incoming messages. So yeah, they won't send like one packet that's like megabytes of data or something like. They'll divide it into like smaller packets, of course. Compressing outgoing blocks and decompressing incoming blocks, optional. So yeah, it's like, I guess, gzip and whatever, like broadly, for example, this website, network. Basically in the HTTP header you can tell it that you want the data encrypted, so like compressed in a certain format like gzip, deflate, zstd, whatever. So I'm guessing that's what they're talking about. Applying a message authentication code MAC to outgoing messages and verifying incoming messages using the MAC. Encrypting outgoing messages and decrypting incoming messages. Okay. So is there a way I can look at the actual API for it. Win32 TLS security API. It's like secure sockets. Yeah, secure Winsock programming. Using SO reuse address and exclusive address use. Okay, the secure socket extensions to Winsock allows the socket application to control security of their traffic over a network. These extensions allow an application to provide security policy and requirements for their network traffic and query the security settings applied. For example, an application can use these extensions to query the pure security token that can be used to perform application level access checks. Security socket extensions are intended to integrate the services provided by IPsec and other security protocols with the Winsock framework. Prior to Windows yada yada yada, applications can already secure network traffic by using public APIs such as IPsec management, Windows filtering platform, and Security Support Provider Interface (SSPI). However, using these APIs may make the application more difficult to develop. May make it more difficult to configure and deploy. The Winsock secure socket extensions have been designed to simplify the development of network applications that require secure network traffic by letting Winsock handle most of the complexity. Curious about IPsec because I think that's what this is using. IPsec. Just sec. Yeah, just security and SChannel what they're using. Interesting. So what's Win32 IPsec? Okay. Okay, this is something else. Like, it has nothing to do with TLS, it looks like. It's more like for securely transferring packets. It's something to do with IPv6, which we don't care about. Secure channel. Secure channel. support. These are the error messages. Error code for SChannel. I saw something from sec e. Yeah, that's what they're checking here. It's everything related to SChannel. So yeah, let's, I guess, include that stuff. That's what we care about. Just security. Include SChannel. Fine. Security. Win32. Chat is too big. This one I don't know if I need. If I really need. So. Sage LW API. Let me just Google it for a second. This header is used by the Windows shell. It's like shell API or something. Interesting. This code. So this consoc should be SCoc. SCoc equals socket. See, in their example, they're just calling socket directly. Yeah, and then they're connecting, they're using WSA connect by name. Interesting. And the code I was following, they were doing it differently, which they're using get address info. In the sample I followed anyway. And this gets all the IP addresses. IPv4 or IPv6 for that. Oh, hello, sausage fist. Really? That's insane. So how was it? Was it easy or hard? Or is it just the documentation that sucks? Anyway, welcome to my stream, Sausage.
This world has room for everyone.
Sock.
Good Earth is rich. It can provide for everyone. The way of life can be free and beautiful.
Figure out if there's any issue in here. The address info, I think this one should be pointer actually, not result. I don't know why they're using result here. My God. I don't think that should be closed in the loop, because if that socket is, let's say, I can't connect to that specific socket, you know, on that IP, with that IP address, then I shouldn't really have to read the address info. I think that's just like in case of an error. Yeah. I really don't like copy pasting code. Like, I'd rather go through step by step, like what each function does. Because the goal at the end of the day is just to learn, you know. The bot is like just a side thing. Like, the whole point with this is to learn sockets. Yeah. I think what this does, this get address info. I did this yesterday. It gets all the IPs for the host and the port that you give it. And yeah, using the hit, so you can tell it like you want TCP, protocol, and what type of socket you want, and I think so. And it gives you like a linked list of address info. And then what you want to do is just check all of them. So set pointer equals to result while the socket is invalid, and yeah, no, the socket is initialized, so this is just comma operator. So socket is set to invalid and pointer is set to result. Pointer is not null and socket is still invalid. So as long as the socket is invalid, it's gonna keep looping. And it iterates by setting the pointer to next. Then here it tries to create the socket with that, you know, the family socket type protocol. And if it's invalid, then it's just this here is just quitting the whole application. So actually it shouldn't do this. It should maybe leave the loop or just like continue. No, I think it should just continue, honestly. We can print the error. I can print the error. And here. It tries to connect to the server here. So if I did it so if there was an error, so I close the socket and it sets the socket type to invalid. You know, I should move this out. Instead of using continue, I moved that out. And I put the connect check inside the other if. And here we check if it's not equal to invalid socket. And here it checks if there was a socket error. Okay. So, what kind of project are you working on? Initialize SChannel. SChannel cred. Channel cred version. W flags. Let's see what destruct's definition is. Contains the data for an SChannel credential. Oh, this is deprecated. Damn. You need to use this instead, I guess. SCH credentials. SCH credentials. Creds. Structure contains initialization information for an SChannel credential. Okay. The version is always just this SCH credentials version. Credential format. Kernel mode SChannel supports the following values. Okay, I guess we just ignore this. Ref pointers to assert context structures. Oh, interesting. Yeah. No, it is interesting for sure. It's a little bit low level, but what option do you have, you know? Except, you know, using some third-party, some huge library. And what's the fun of that? You know, you don't even know what you're doing. Oh yeah, for a game server, you'd probably just use like UDP, because the performance is very important for networked games. Like even AAA games, they just use raw UDP packets. Yeah. EW flags. Let's read this. Yes, true. I'm interested in this because I'm slightly interested with security also. Not really that much. Like usually I work on rendering stuff, like not networking. I'm doing this because it's good, you know. I can learn some new stuff, and it will help me later on. Yeah. Oh my God, I need some tea or something. Actually, I didn't have breakfast or anything. I just wanted to stream, you know. Maybe I'll go get some coffee or tea. Just see what flags they use. So they use SCH strong crypto. SCH use strong crypto. Instructs SChannel to disable known weak cryptographic algorithms. Cipher suits and SSL TLS protocol versions that may be otherwise enabled for better interoperability. Let's check this one. Client only. This flag is opposite of manual cred validation. It's opposite of this. Prevent SChannel from validating the received server certificate chain. Okay, we want it to be automatic. Just copy paste this because I know what it does. GR bit enabled protocols SP prot TLS 1 2. Wait, I think they removed this from the, because This isn't in the new struct. So it's either called something else or there's a different way of PTLS parameters. So you have to use array of pointers to TLS parameter structures that indicate TLS parameter restrictions, if any. If no restrictions are specified, the system defaults are used. It is recommended that applications rely on system defaults. We can either tell it like what to use as a restriction or just use the defaults. I don't think this is it though. There's no version in this structure. Oh no, there is. There's GR bit disabled protocols. Not GR bit enabled protocols. Yeah, let's just leave it default. Yeah. Let's just do defaults. Then they're calling acquire credentials handle. If acquire unisp sec package cred outbound null cred null s handle. So if that's not sec e, okay. Low socket, yep. Say cleanup. Turn -1. Just look at this function. So this function acquires a handle to pre-existing credentials of a security principal. Pointer to a null terminated string that specifies the name of the principal whose credentials will whose credentials the handle will reference. Package pointer to a null terminated string that specifies the name of the security package with which the credentials will be used. This is a security package name returned in the name member of a sec package info structure, returned by the enumerate security packages function. Isn't Win32 great? It's so good, bro. Credentials use. Validate an incoming server credential. Inbound credentials might be validated by using an authenticating authority. Yeah. Yeah. So what language were you using to write your program? I'm just curious, like.
You all have interesting characters, but some of them are all hidden. I wonder why you all want to dress always the same. The same hats, the same coats. I'm sure all of you are interesting and have wonderful things about you. But looking at you in the street,
Ah,
you all look so much
UNISP. Oh, Odin.
try and express yourself.
That's really good. It's a decent language. PSZ package. It's pointer to a zero terminated string package. So I'm guessing this is just like a macro. It's UNISP name A. Wait, let me control enable package. Can I find this somewhere? Oh yeah, this is the definition, see. Microsoft Unified Security Protocol provider. And I just realized this struct is not compatible with this function. Lol. SChannel use blacklists with Unicode string and P Unicode string alternatively. Okay, so we have to define this. Fine. SChannel use blacklists and fine. Unicode string. Okay. Oh, I see. Wait, where is it? Yeah, here. Enumerate. Enumerate security packages. I see, but this one's like guaranteed to always exist or something, right? This Unisp name A. Okay, so I'm guessing it's like Unicode security package, right? Like. I'll be right back. I'll get some tea. Or coffee. I'm back. Okay, so I assume it is always there if SChannel is there, i.e. it is the security package that provides SChannel functionality, and so if that string isn't valid, then it means SChannel would not have been available on that machine anyways. Okay. Sure. You're saying it says it here? Mentions what value to use for SChannel. LW was on your screen just now. Okay, Unisp. Oh, okay, I see. Yeah. When using the SChannel SSP, set this parameter to... Yeah, okay. So SSP is like security security protocol provider. Microsoft Unified Security Protocol provider. Okay, and that's the value for SChannel. Okay, I get it now, I get it. But I think this function, it doesn't work with this new struct. I don't know which function works with it. Mm, oh, acquire credential handle W. Really? Let's see. Wait, no, it does work. Cred handle. No, it's not cred handle, right? It's 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, it's auth data. Auth data. Pointer to cred SSP cred structure. No? Yeah, it's just void pointer. So it could be either one, like. But how does it differentiate? I'm just curious if it can just differentiate it by itself, or if we have to set something. I guess just both are valid. Yeah, I don't think it matters, right? Let's make it void star. Let's go back to the code. So then he's setting received. So how many bytes were received to S used to S available. So all of it is 0. And decrypted is null. Oh, I didn't see that, Ibrahim. Thanks for sending 100 bits. I didn't see it earlier. Thank you. Perform. Yeah, perform TLS handshake. So I'll initialize security context to create/update SChannel context. When it returns sec EOK, and TLS handshake is completed. Okay, so now let's look specifically what this function is supposed to do. Hmm. It's also, how long you been learning Odin? And, writing code in Odin. So what does this do? The initialize security context function initiates client-side outbound security context from a credential handle. The function is used to build a security context between the client application and a remote peer. Oh, that's great. That's great. And what language were you using before? C? I see. Really nice. You know, I'm doing this because my main project is like, it's written in C, and it's a library actually. It's getting pretty big. I would say it's like it's over 10,000 lines of code for sure. And on that project I have to work on something it's even more just wrecks my mind than this, which is decompression, like broadly decompression. I've been just trying to find like a free, you know, debugger that I can use, like instead of using VS or something, you know. But I'll probably just use VS to debug that project once I decide that I want to work on that. Yeah, I'm working on the like font shaping library. But I'm not working on it on stream because I don't want people to just watch me struggle for 8 hours, you know, trying to figure out like how to decompress like a bit stream, you know. I decided to skip, you know, TTF. I decided to skip the TTF file format because I feel like there's no point anymore. Like the TTF files are pretty huge in size. So I was thinking, yeah, I'll just do WAF 2, you know. And no, it's not for need. It's just a project that I want to do. Like I don't really have. I had an idea for an application to make with it, but it's not like I really have any idea what to do with it now. But what I wanted to do is just make it simpler to do shaping. You know, because if you use something like Harfbuzz or Uniscribe or something like that, you have very little control. And I made it like work without the standard lib. You know, I managed the whole allocation, memory allocation, like better than those other libraries. At least Harfbuzz. I don't know Uniscribe because I think it's closed source. Not sure. This is the project. Yeah. Anyway, it's that's my main project, but if I work on that on stream, nobody's gonna watch my stream. It gets pretty complicated, and also I'm very picky when I like not very picky but very perfectionist with the code. So Like, I like to understand things before I write them. I could just write it, you know, like at some code already for decompression and all that, but I want to understand the code fully for implementing anything. Oh, nice. I'll look at it. So you just like give it a PDB file and it can debug. Anyway, I'll look at it later. So I've downloaded it. So is it like CLI based or is it visual? Oh, nice, nice. Yeah, I'll definitely look at it, like, after stream, you know? So I'm just tired of using VS, honestly. I can't stand it, even VS Code. Yeah. GUI, of course. But you have to pronounce it GUI. GUI. I'm just kidding. Let's go back to our code. So interesting, he's setting the context handle to null. And int as a result equals to 0. Or sec buffer. Initialize security. Context stay. First thing is the cred handle, which is this. I don't know why it's a pointer to it. I have to give it a pointer. Like, is it gonna modify it or something? Oh, it's weird. Thanks, Ibrahim. Welcome back. Thanks for giving 100 bits earlier. PC text handle. PC text handle. Here's the... It's like a pointer to the context. Interesting. Or no, just the context. Context. Target name. Okay, so this is basically if it's already initialized, then we set it to null. Otherwise, okay, otherwise it's a host name. So yeah, if it's not initialized in the first iteration, it will create the context. Context rec. Context rec. Yeah. I see. Flags. Just gonna copy paste these flags for now. Reserved. Yeah, it's just gonna be 0. Target data rep. Isn't this also 0? But why? We close everything. Data representations such as byte ordering on the target. This parameter can be either security native drep or security native drep. Parameter is not used with digest or SChannel. Okay, so if you use SChannel, it's just 0. It's good to know why these parameters are what they are, you know. Sec buffer description, so in desk out desk. Yeah. course. It's always like that with Win32. Has to be like that. On 0. It's the context. So if it's not null, then this is in desk. Otherwise it's null. Interesting. I don't get, honestly. I'll get this part. Oh well. Like we're just creating a sec buffer and it's just like one of them is set to token. There's the incoming and received. I guess that's the buffer data and the size. And then the second one is just sec buffer empty. Honestly, I don't get it, but maybe later I will. And this is probably just out desk. Should be here. This thing. Hero context. Yeah, and again, context null, or else it's the this time S context. Yeah. Actually, there is a reason why those flags they were outside. PF. Yeah, flags. Expiry. Expiry. Your first call to initialize security context. Context is available and should be reused for next calls. Yeah, so context is just S context. If in buffers sec buffer extra. Sec buffer extra. Extra buffers returned by SChannel. But before this, I'll look in here again. Let's just read this documentation of those arguments. Pointer to a CTX handle structure. The first call to initialize. Yeah, this pointer is null. On the second call, this parameter is a pointer to the handle to the partially formed context returned in the ph new context parameter by the first call. This parameter is optional with the Microsoft Digest SSP. When using SChannel SSP on the first call to initialize security context, specify null. On further calls, specify the token received and the ph new context parameter. After the first call to this function, specify the token received and the ph new context parameter. Here's the doc for when this function is used in the context of SChannel. Let's see. Okay, so that parentheses. Okay. Yeah, this one tells you that's SChannel. Interesting. I didn't know that they had a page for each, like when using each API. I guess this is like a security provider. Yeah. So handle to the credentials, yeah, ph context. This pointer is null. On further calls, this parameter is a pointer to handle to partially formed context. Yeah, that's the same thing. I see, so it's gonna be null, but the next, when we set it afterwards, we're setting it basically for the, so that on the next iteration it's not gonna be null anymore. So we're gonna be able to yeah, we're not gonna have to set the host name anymore. And this last context param, it's also gonna be null. So this is just like a clever way that they done this code. So basically the first iteration, it writes to the one in the struct, TLS socket. Then from the struct they set it to this context variable here. And so every iteration it's gonna use that to check that if we need to set this host name, or if we have to create the context. So we pass this, otherwise we pass null. And same for indesk. I see. Wait. So p input, a pointer to a sec buffer desk structure. Pointer to sec buffer desk structure that contains pointers to a buffer supplied as input to the package. Unless the client context was initiated by the server, the value of this parameter must be null. Okay, so I see. So that's why here they're checking if it's null. We're passing it. Okay, so there's p output. Pointer to, yeah, that contains pointer to sec buffer structure that receives the output data. If a buffer was typed as sec read write in the input, it will be there on output. The system will allocate a buffer for the security token if requested. Yeah, through this flag, iscrec allocate memory, and fill in the address in the buffer descriptor for the security token. Interesting. The ISC, so in that case it would allocate the memory. Oh, but in this case, Oh no, that's the input. That's the input. This is output. So an output we're telling that we want them to allocate the buffer for us. That has the token. Pointer to a variable to receive a set of bit flags that indicate the attributes of the established context. Okay. We're still using the same D word. So yeah, I'm guessing the flags after, they have no relation to the ones we put in, like it's a different thing completely, right? But they're just using that D word. Am I right on that? Oh, okay, it says just here, ISC ret. So I just prefixed that. Prefix with this. I see. Not check for security related attributes until the final function call returns successfully. Read flags that are not related to security, such as can be checked for the final return. ASC ret allocated memory. Copy this. Oh. So check if there is extra data. If in buffers buffer type is sec buffer extra. They're moving the memory, or part of the memory. S incoming. S incoming plus S received minus. That's how many bytes we received. Minus. CB, the count, the buffer. So it's like shifting, moving that memory down from the end of the incoming buffer. Why though? That's that's the question. S incoming plus S. Received. Alright, thank you. There's one CB buffer in buffer. There's one dot CB buffer. S received. There's one CB buffer. So we're basically just discarding the start of the message. Information must be sent between the client and server. A security context is being established, and afterward, the secure messages are exchanged by using the encryption and decryption features provided by SChannel. The following functions are used to accomplish these tasks. SChannel has a well-defined set of behaviors for incomplete or excess information included in the input buffers to these functions. For incomplete or excess information included in the input buffers to these functions. Information is exchanged between the client and the server in the following manner. Local party interacts with SChannel by calling an SSPI function and passing in information. Typically, the information was received from the remote party. The function returns the status code and output buffers containing information. Depending on the status code, the output buffers are sent to the remote party by means of some communication mechanism. The remote party reads information sent by the local party. The loop repeats, with the local and remote parties interchanged. The remote party calls an SSPI function and passes in information read in the previous step. The loop repeats, with the local and remote parties interchanged. The remote party calls an SSPI function and passes in the information read in the previous step. I see, so it's like two pointers, and after each iteration those pointers are swapped or whatever for the local and remote parties. Everything works as expected when the input buffer to the SSPI function contains exactly information needed. However, due to the stream-oriented nature of some communications protocols, this may not be the case. A block of information received from a remote party may contain less data that is required or more data than can be processed by SChannel in a single function call. Interesting. If the input buffer contains too little information, functions return sec-e incomplete message. Caller must obtain additional data from the remote party and call the function again. I see. When the input buffers contain too much information, SChannel does not treat this as an error. The function processes as much of the input as it can and returns the status code for the processing activity. In addition, SChannel indicates the presence of unprocessed information in the input buffers by returning an output buffer of type secBufferExtra. Okay, I see now. So it writes directly into the buffer. So it knows that in the next iteration it has to... This is part of the continuation from the last message, right? Testing the output buffers for this type of buffer is the only way to detect this situation. The CB buffer field of the extra buffer structure indicates how many bytes of the output, how many bytes of input were not processed. Interesting. Okay. So it's pretty simple actually. Else as received Sec. Well, sec E. Okay. Break. It makes sense, like it's just in case the handshake is already complete. Yo, welcome Sorrow Riffs. Complete credentials. Complete credentials. Server asks for client certificate, not supported here. Okay. Salt was -1. Break. Hello. We're just working on just a regular chatbot for Twitch. I'm doing it in C and I'm writing it from scratch on Windows. And we're trying to do TLS from scratch, you know, without using third-party libraries. All I'm using is just the Windows API, not doing anything extra. Sec elsif sec I continue needed. Need to send data to the server. Oh, nice. That's really good. I mean, C#. It's not really a bad language to start with. Is it your first language, or are you just learning C# as an extra language? So interesting. And what languages do you know already? Interesting. Are you learning it for like game dev or something? Or for making applications or. Sharp is like, it's typically used for making applications on Windows. From what I've seen. But I've seen it also used in games. Because it has like native support with like MySQL. Not MySQL, like Microsoft SQL Server or something. Using C# in Unreal. I don't know, I never heard of that. I thought Unreal was C++ only. Oh, you meant CPP? Oh my god, okay. Yeah, CPP is used a lot in game dev. There's a pretty good book if you want to learn like pointers. I don't know if like what level you're at, but if you haven't learned pointers yet, I have a pretty good book about that. It's for C, but it applies to both C and C++. It's the book. It's called Pointers in C Programming. Modern approach to memory management, recursive data structures, strings and arrays. Yeah. It's pretty detailed, like teaches you everything like about memory structs, alignment, call stack, what type of memory there is, like how arrays get stored on the stack, on the heap. Like alignment. My friend is using this book to learn C. I'll copy the title. Yeah, it's a pretty decent book. And at the end of the book, like you implement, like it goes really deep even at the end, like teaches you about dynamic memory management, string operations, dynamic arrays. Like you learn like how all of this stuff works at low level. Gapped buffers, void pointers, linked lists. Yeah, this is like data structures after, like singly linked list, doubly linked list, sorting, selection sort, insertion sort, merge sort, quick sort. Yeah, it's a really good book from what I've seen. Sec I continue needed. There's incomplete message. So only these two left. These two cases. Not really sure what this means. This continue needed. Yep. Yeah. Clients must send the output token to the server and wait for a return token. The return token is then passed in another call to initialize. The output token can be empty. The client must send the output token to the server and wait for a return token. But what kind of token is this, like? Do you have any idea? For size. Sending it directly like on the socket. I see. Send that data to the server, receive data from the server, and put that received data in the input buffers when call the initialize function again. And the sorrow riffs, nice. And yeah, I've been working on as a project test a standard turn-based RPG in VS. It feels good to get a code working properly. Yeah, it's a good project to start with. So while size is not 0, okay, so it's just sending it like these how many bytes were sent. So if D is less than 0, then break. Interesting. Okay, you could do it like also this way. don't know if this is better or... we don't need those parentheses. Those curly braces, sorry. Thanks for following, everyone. Our Riffs followed, Blowfish, Fugu, Yusepe, and Bush, QRDX, TCAP, Mo22J. Thank you all for following me. And thank you, Sausage Fist. Practice, then the result will be a TLS handshake. First call to function puts a client hello message to the output buffers. Server will send server hello in response, so that you will then pass to the function again. Okay, I see. So that's how it does it, like step by step. Size minus equals d, buffer plus equals d. So it just sends the raw bytes from the output buffer to the server, or through that socket, which means it would connect to that host, I guess. Context buffer or PV buffer. This makes sense. Size is not 0, result -1. Failed to fully send data to the server. Okay. I'll just... I guess just one case left now. Yeah, I see. Just like a black box, kinda. Complete message. IFSEC is not equal to incomplete message. It means we've had an error, which can be either certificate expired, wrong principal, which is basically bad hostname, untrusted root, cannot verify CA chain, or yeah, illegal message or algorithm mismatch. Interesting. So I'll keep that because I might want to check these individually if we're getting errors later on. So yeah, read more data from server when possible. If S received, size of S incoming. Result is -1. Break. Yeah, so if data is exceeding our buffer basically, or it's equal to it, which means, yeah, it basically means it's exceeding it. So then yeah, server is sending too much data. Makes sense. And R ResV, this is gonna read from the socket. S incoming plus S received. Okay, let me check this function again. The socket, the buffer, and the length. Socket. They're moving it forward though. Moving it forward by received. That was preemptive. It's byte, changing this to byte. To actually be char. For some reason ResV takes a char pointer. I really don't get sometimes these APIs. Yeah, let's see. Return value. If no error occurs, ResV returns the number of bytes received and the buffer pointed to by the buff parameter will contain this data received. If the connection has been gracefully closed, the return value is 0. So now actually if it was closed gracefully, the return value is 0. Wait, what? Oh yeah, okay, no, they're checking if it was closed, if the socket was closed. That's why they're doing this. And I honestly don't know why here they're returning. They're just returning 0 from the function. Honestly, I don't get it. Oh, I guess, yeah, I see, because he's checking if result is not equal to 0. Then he's like deleting the context, free credentials, close socket, WSA cleanup. But in the case where I think closed means like closed properly, right? Gracefully closed, like basically the server caused the socket to close. Still, I don't know. I don't know why he's returning directly and he's skipping this one. He's skipping it anyway, but this line, he's skipping this line in this case. Yeah. I need to step through it with a debugger to know. Music stopped. Result is -1, break. S received plus equals R. All of this should be commented out for now. Or I just do if 0. It's better. If result is not 0, then it just destroys all that those objects. Query context. Attributes, context, sec package, attribute, stream sizes, S sizes. Let's see what this is. SChannel, sec package. Attribute stream sizes. Attribute stream sizes. The buffer parameter contains a pointer to a sec package context stream sizes structure. Here's the sizes of the various parts of a stream used in the per message functions. I'm checking the error because for some reason they weren't checking it previously. That's just this one function, TLS connect. And here in main, they're trying to connect to google.com. Let's just do the minimal example here. Which host name? This one 443. It's not 0, then yeah, error connecting to host name. Otherwise connected. But it has a path as well, which path is I had it somewhere. Yeah, it's still here. All of it's still here. His name, port. Port is actually a string though in this. Just change it. Change this to a string also. Move this outside. I don't know why they made it a string, like, isn't it ridiculous? Like, why would the port just be a string when it's in reality it's an integer? Oh, okay, because it's generic, so it can either be a service or a port number. That's in case like you wanna say connect to a, I guess, a service on the system. Okay, I see. Interesting. I could say like HTTPS, for example. Here. id.twitch.tv. OAuth2 token. This added onto it. I'll keep it safe, I guess, just 443 instead, for now. Okay, I don't think it's gonna compile because I need to include those lib files. And yeah, what's this? P Unicode string, unknown type name. Is it P Unicode string? Sharp pointer. Yeah. Nah. I'm guessing in Odin you don't have to do any of this. Oh, okay, it says it right here. You must define security Win32. Not sure. I think it's just clang D that included it. Why? Why did I write the same message again? Oh. You just clang that's clang D that included that. I don't really need it. I guess we need Windows.h, fortunately. Mean and mean. Good. Windows.h. Nope. Something in this channel. I have to define like Unicode string. Unicode string. I have no clue if this is correct. Sure, let's try it. Nope. Yeah, you need this security 132. It says here, you must define one of security 132, security kernel, or something. Security Mac. So yeah, that's a must. Now this, it needs these types, Unicode string and P Unicode string. I have no clue where, if I'm supposed to define it like this or... Oh, it's in NT-def. Okay, so... NT def.h. No? There's a conflict if I use NT-def. Yeah. He's including security below, maybe that's why. He's not using this use blacklist define. However, I think I might need that because, yeah, because I'm using the struct instead. Yeah. But then I get these errors if I use blacklists. Let's read the docs again. To use SH credential structure, define SChannel, use blacklists along with Unicode string and P Unicode string. Alternatively, include ntdef.h, subauth.h, or winternal.h. Yeah, no. Just because of win error. No. Strings, so I have to define them. New code. Oh, okay, just this. Let's just do it ourselves. Right here. Okay, it works now. This is ridiculous. Swear to God, sometimes I don't understand Windows API. Why do I need to define a structure on my side? Like, oof. Error at socket. Just a logic error. Connected. Nice. So wait, can we like send messages now? I'm guessing we still have to use the same API to actually send messages. Yeah, and we have to encrypt it. Encrypt message. I see, so basically all the information like the RSA key or whatever, not RSA, sorry, AES is the most common. It's just saved inside this context object, right? And it uses that to encrypt the message. And then you can send it, yeah, you send it through the socket. Yeah. Yeah, so the hardest part is just that handshake. And then it's smooth sailing from there. Let's do TLS disconnect. If you hang around, I'll show you my other project. My font shaping project. TLS socket. Keyword type. Channel. Shut down. Intolerance. For desk, in desk. For version. Buffers. Inbox. Apply control token. SChannel. The apply control token function provides a way to apply a control token to a security context. Context can be received. Token can be received when the security context is being established by a call to. Yeah. Okay, the function is supported only by SChannel. Pointer to a sec buffer desk structure that contains a pointer to a sec buffer structure that contains the input token to apply to the context. Okay, so the token is this channel shutdown. Okay, so we're telling the context that we want to shut down basically. Right. And we want to check it's not sec E okay. We have sec buffer. Buffers 1. Oh.
His senses and time perception are distorted.
C rec. They detect. I see rec. Stream. Interesting. So even to disconnect, you need to call this function. Initialize security context. It's interesting, you know, it's interesting. Interesting. Honestly, really curious, like, why? Why does it need to send it, like, using this function, this initialized security context? No, I guess this library tells us what we must send the server to shut down, basically. Yeah. Interesting. That's what this buffer and size are, even the other one. Send. Wait, couldn't it just be a while loop? I mean a for loop? Pretty sure it could. No. Never mind. D equal send sock buffer suppose maybe if the shutdown could be sent outside the secure context and anyone would be able to send disconnect please back to the server, yeah. That's what I was thinking too, like. It probably has like a disconnect procedure. It's like it has that handshake. For when you connect, you know. Or context buffer. Shut down. Sock. Security context, free credentials handle, and close socket. Interesting. Just do this now to make the program safe. Exit safely. Printf. Disconnected. Oh. What did I do? Oh, it has to be this clang D, bro. Disable. Clang D. Enable package. Easy clang complete. Return 0. Yeah, nice. TLS right. Just take a break for a second and we'll do TLS right and then TLS read. TLS read is quite complex. Maybe I'll do it next stream or something. I did more than I wanted to do anyway on this for today. Alright, be right back. I'm back from my break. Yeah, when it comes to this project, pretty much done with it for now. At TLS connect and disconnect. Not sure I can push right now. Not really. Yeah. Maybe with GitHub desktop. Right. Push. Alright, I pushed it. I pushed it. So yeah, I'm done with this for today.